February 2015, Felts Field, a quiet airport on the edge of Spokane. A pilot ran his checklist. Customs cleared. Destination, California. The engine turned over without hesitation. The instruments read exactly what they should. He taxied to the runway and lifted off. 3 minutes into the climb, the engine stopped. Not a sputter, not a warning, just silence. The wreckage came to rest at the bottom of a railway embankment. When investigators reached the scene, they noticed something before they opened a single logbook. The smell, not avgas, kerosene. The answer wasn't in the engine, it was in a fuel log. 52 gallons of the wrong fuel, loaded, logged, and never caught. The safety system designed to stop exactly this was in place. It just wasn't enough. What that fuel did inside the engine, why the pilot had no warning, why a system built specifically to prevent this mistake failed anyway. That is what this is about. Not all fuel is the same. Commercial airliners run on Jet A, a kerosene-based fuel, dense, slow-burning, designed for turbine engines that operate at extreme temperatures and altitudes. Piston engine aircraft run on avgas, a high-octane gasoline, chemically different, engineered specifically for engines that ignite fuel with a spark. Two fuels, two completely different engines, and they are not interchangeable. It is not unlike putting diesel into a petrol car. The engine accepts it. It does not immediately stall. It does not throw a warning light. For a few moments, everything feels completely normal. That is exactly what makes this so dangerous. When Jet A enters a piston engine, the engine doesn't stop. Not right away. It keeps running. The instruments stay normal. The pilot feels nothing unusual. The plane climbs, and somewhere inside the engine, something has already begun to fail. The question is, what exactly is happening in there? And how much time does the pilot actually have? Inside a piston engine, combustion is a precisely controlled event. The fuel ignites at exactly the right moment, burns at exactly the right rate, and pushes the piston down with a steady, predictable force. The entire system is calibrated around one assumption, that the fuel inside the cylinder is avgas. Jet A changes that assumption completely. Jet A has a much lower octane rating than avgas. In a piston engine, low-octane fuel doesn't burn smoothly. Instead of a controlled burn that pushes the piston down in an organized way, the fuel-air mixture explodes. Not burns, explodes. This is called detonation, and detonation doesn't announce itself. The instruments in the cockpit show normal readings. The engine sounds normal. The plane is climbing normally. But inside each cylinder, the fuel is detonating rather than burning, sending shockwave after shockwave directly into the piston face. Imagine hitting the top of a piston with a hammer, repeatedly, hundreds of times per minute. The piston face begins to erode. The metal starts to pit and crack under the repeated impact. Cylinder head temperatures climb, not gradually, but sharply. The rings that seal the piston to the cylinder wall begin to fail. Combustion gases that should be pushing the piston down start bleeding into the crankcase instead. Then the connecting rods, the components that transfer the piston's motion to the crankshaft, begin to bend under the stress. Once a connecting rod fails, it doesn't fail quietly. It punches through the engine casing. Oil pressure drops instantly. What remains of the engine seizes. According to aviation safety investigators, engine failure from detonation can occur within minutes of takeoff, not hours, minutes. Here is what makes this truly dangerous. The pilot had no warning. No warning light, no unusual sound, no vibration. The cockpit gave no indication that anything was wrong. The engine ran, climbed, and performed, right up until the moment it couldn't. And this is exactly what happened in Spokane. The pilot in that fuel log, he had a name, a destination, and no idea what was already happening inside his engine. Michael Clements was 61 years old and flying south. He had departed from Alberta, Canada, on a cross-country flight to California. Felts Field in Spokane, Washington was a routine stop. Customs clearance and a fuel top-up before continuing the journey. Nothing unusual, nothing complicated. Just another stop on a long flight. On the afternoon of February 22, 2015, Clements requested fuel at Western Aviation, the fixed base operator at Felts Field. He did not specify a fuel grade. He didn't say avgas. He didn't say Jet A. He simply asked for fuel. Felts Field was not a simple airport. It was home to a company that specialized in turbine conversions, taking piston engine aircraft and converting them to run on Jet A. The ramp regularly handled both types of aircraft. The line technician who serviced Clements's Piper PA-46 that afternoon made a decision based on what he saw in front of him and loaded 52 gallons of Jet A into a piston engine that required avgas. Clements taxied to the runway. The engine sounded fine. He lifted off and began to climb. Within minutes, the engine experienced a total loss of power. Clements had no runway ahead of him. He attempted an emergency landing in the only space available. The right wing struck a set of railroad tracks at the top of a hill. The plane continued down the embankment, the wings separating from the fuselage, coming to rest inverted on the road below. Witnesses on the ground described the engine sputtering, the left wing dropping, the nose pitching upward, and then the right wing striking the tracks. First responders who reached the wreckage reported a strong smell of jet fuel at the scene. The fuel tanks had ruptured on impact. Michael Clements died at Providence Sacred Heart Medical Center on February 24, 2015. The NTSB investigation confirmed what the fuel log already showed: 52 gallons of the wrong fuel, loaded on the ground, before the plane ever left the runway. But here is the question that the investigators had to answer next. How was this even possible? Because the aviation industry had already built a system specifically designed to prevent exactly this mistake. To understand how the system failed, it helps to understand how the system was built. The story begins decades earlier, at an air show in San Diego. It was 1978. Bob Hoover, one of the most celebrated aviators in American history, climbed into his Rockwell Shrike Commander at Brown Field for a performance. Hoover was not an ordinary pilot. He was a former World War II fighter pilot, a test pilot, and a man widely regarded as one of the greatest stick and rudder pilots who ever lived. Just after the aircraft left the runway, at approximately 300 feet above the ground, both engines failed simultaneously. Hoover managed to bring the aircraft down onto the side of a ravine. The plane was severely damaged, but Hoover and his 2 passengers walked away from the wreckage. While waiting for rescue vehicles on the hillside, Hoover walked back to the aircraft and leaned in close to the fuel tanks. He smelled kerosene, not avgas, kerosene. A ground crew member had mistaken his piston engine aircraft for a turboprop and filled it with Jet A fuel. The aviation industry took notice. What followed was one of the most practical safety interventions in general aviation history. Engineers redesigned the physical interface between fuel trucks and aircraft. The fuel filler ports on piston engine aircraft were standardized at less than 2.36 inches in diameter. The nozzles on Jet A fuel trucks were redesigned with a flattened, widened spout, at least 2.66 inches across. The geometry was intentional. A Jet A nozzle physically cannot enter a standard piston aircraft fuel port. The sizes don't match. On top of that, color coding was introduced across the industry. Avgas 100LL was colored bright blue, unmistakable, distinctive, impossible to confuse with anything else. Jet A remained clear with a faint straw color. Fuel trucks were labeled. Aircraft fuel ports were placarded with the words "Avgas only." Checklists were updated to require pilots to verify fuel type before every departure. The industry had looked at the problem, identified the failure points, and engineered them away. Misfueling on paper had been made physically impossible. That was the theory. The reality was different, because in 2015 in Spokane, a piston aircraft was loaded with 52 gallons of Jet A. And 4 years later, the same mistake happened again, in a way that should have been even more impossible than the first time. Daniel Greenwald was not a casual pilot. He was 59 years old, a successful plastic surgeon based in Tampa, Florida, and a highly experienced aviator, a former designated pilot examiner, a man who had spent years evaluating other pilots for their certifications. On the morning of October 5, 2019, he departed Tampa's Peter O. Knight Airport at 6:45 a.m. in his twin-engine Piper Aerostar. He was headed to Kokomo, Indiana, to provide flight training to another pilot in a different aircraft. He arrived at Kokomo Municipal Airport at 10:27 a.m. The employee who came out to service the aircraft was a college senior majoring in communications. It was his first job in aviation. As Greenwald approached on the radio, The employee looked at the Piper Aerostar on final approach, a sleek, low-wing twin with a distinctive profile, and made a decision. When Greenwald taxied in, the employee asked him directly, did he want jet fuel? Greenwald said yes. The employee drove up in the Jet A truck. The truck was clearly marked. The nozzle on that truck was the widened, flattened Jet A nozzle, the one specifically designed not to fit into a piston aircraft's fuel port. The employee asked again, just to be sure, did he want jet fuel? Greenwald said yes again. The nozzle was not supposed to fit. The geometry of the system, the entire physical safety mechanism that the industry had built after Bob Hoover's accident, was designed to make what happened next impossible. The employee tilted the nozzle approximately 90 degrees, angled it against the fuel port, and forced it in. He spilled roughly 1 gallon of Jet A on the first attempt. He adjusted his technique. The rest went into the tanks without spillage. Greenwald took off shortly after. Both engines failed. The Aerostar entered an aerodynamic stall and lost control. It came down in a soybean field, 3.5 miles south of Kokomo Municipal Airport. Daniel Greenwald did not survive. The NTSB confirmed that the aircraft had been fueled with Jet A. The spark plugs recovered from both engines showed damage consistent with detonation. A clear liquid consistent in color and odor with Jet A fuel was found in the fuel lines and manifolds of both engines. The system had been there. The physical safeguard had been there. And someone had worked around it with a 90-degree turn of a nozzle, which raises the question that the aviation safety community has been asking for decades. If the system can be bypassed this easily, why hasn't it been fixed? The honest answer is uncomfortable. The physical safeguards work. The color coding works. The nozzle geometry works. On paper, the system is sound. But the system was designed around a set of assumptions, and humans have a remarkable ability to work outside assumptions. At airports, that service both turbine helicopters and piston aircraft, fuel truck nozzles are sometimes swapped. A Jet A nozzle gets replaced with a smaller nozzle to service a turbine helicopter that doesn't have the standard oversized port. The job gets done. The nozzle doesn't get swapped back. The next aircraft to pull up gets whatever nozzle happens to be on the truck. Then there are aircraft that have been modified. When a piston engine is replaced with a turbine engine under a supplemental type certificate, the aircraft now runs on Jet A, but the fuel filler port is sometimes never updated to the larger Jet A standard. The result is an aircraft that looks like a piston plane, has a piston-sized fuel port, but requires jet fuel. Line technicians who don't know the modification history of that specific aircraft have no reliable way to tell the difference from the outside. Miscommunication fills in the rest. Pilots who assume the fueler knows what they need. Fuelers who assume the pilot will correct them if something is wrong. A single word, fuel. That means different things to different people on the same ramp. And underneath all of it, there is overconfidence. The assumption that misfueling is someone else's problem, that it happens at other airports, to other pilots, with other aircraft. The checklist exists, but the checklist gets skipped. The placard says avgas only, but the placard gets ignored. Between 2014 and 2021, investigators documented at least 5 major misfueling incidents involving the wrong fuel type. 5 in 7 years, despite the nozzles, despite the color coding, despite the placards, despite everything the industry built after Bob Hoover walked away from a ravine in San Diego. The system was designed to be foolproof, but it was never designed to be human-proof. And Michael Clements is the reason that sentence matters. Michael Clements had stopped at Felts Field for 2 reasons: customs clearance and fuel. He was on his way to California. He pulled up to Western Aviation, asked for fuel, and trusted that the person holding the nozzle knew what they were doing. He had no reason to think otherwise. No pilot does. The NTSB investigation concluded that the probable cause of the accident was the misfueling of the aircraft with Jet A fuel instead of the required aviation gasoline, resulting in a total loss of engine power during initial climb. Contributing factors included the failure to specify fuel grade and the operational environment of an airport where both fuel types were regularly used. Nobody in that chain intended for Michael Clements to die. The line technician made an assumption. The pilot made an assumption. And somewhere between those 2 assumptions, 52 gallons of the wrong fuel entered an engine that had no way to reject it. The engine ran. It climbed. It performed exactly as expected, for as long as it could. There is no sensor inside a piston engine that detects the wrong fuel. No warning light, no alarm. The engine cannot distinguish between what it needs and what it has been given. The plane doesn't know what fuel it's carrying. It just flies until it can't.